The way that I suggested for writing into the file.
I just don't think I wrote that down.
Okay. Yeah, which you only need to do when you update the tree. And for reading, you just use scanner as usual.
Okay.
So no questions? It's potentially a good sign. So we started talking about regular expressions, is this true?
Yeah.
Okay. So let me just show you a simple piece of code. So the idea here, I just did this for fun, basically, was to be able to write expressions like simple assignment statements. And imagine you were writing an interpreter, like MATLAB or BASIC, and you wanted to be able to parse expressions and process them. So one of the expressions you're going to encounter are assignment statements, right? And a lot of these languages, you don't declare variables. You don't have to declare your variables in MATLAB, for example. They're kind of picked up along the way. When you say I equals 5, it says I must be a variable, right? So typically what you do as you're reading lines of code is you're parsing the line to figure out what kind of statement it is. Okay, so something that's a variable name, an equal sign, something that's an expression, that's an assignment statement. And if you've never seen an expression involving the word time before, then time is a new variable. And you need to somehow record in your program's memory that there's a variable named time and that its value is currently 12, right? So you're creating something like a symbol table, but with an interpreter, you're also recording what the actual value is associated with that particular symbol. And then when you see date equals 20, right, same thing. Date's another number and it's equal to 20. And then when you encounter time equals 25, you need to know that you've already got a variable named time, and you already gave it a value, 12 in this case, but now you want to change that value to 25. And this is, you know, the beginning of an interpreter for whatever language you choose. And doing something like this in Java is remarkably easy, right? Because of, in particular, regular expressions patterns, right, which let us do the parsing pretty painlessly, and things like hash maps that let you build symbol tables that you can key off of a variable name and you can just associate whatever value you have with that. So, and this is all you need to do that kind of basic parsing and processing. So just as another example of using built-in classes to do higher level things. So we have a hash map, okay. Don't worry about static. We'll talk about static in a second, why everything's static in here. But we have a hash map. It's keyed on strings. It stores integers. Okay, so we construct it up here, and it's global to everything else in here. And let me show you the purpose of this code. So when you run this, you can say something like time equals 12 and date equals 20, and you can ask for the value of a variable just by typing in its name. And then if you override time equals 25, right, that's the new value. Right, and it keeps track of variables that are close but different. Right, so nothing terribly startling there. So we have a hash map that's going to store all that information, okay, variable name, value. And to do the parsing, we compile a pair of patterns. So an alpha, right, that's your variable name, is something that starts with an upper or lowercase letter followed by 0 or more uppercase, lowercase, or numbers, followed by the end of the string. So time 2, I7, and so on are all valid alphas. And an assignment statement is something like that, followed by an equal sign, followed by 0 or more digits. I should probably force one digit in there. So it's variable equals value, and it's only positive integers in this case. And we've got parentheses here, right, grouping the pieces of our input string that match this pattern. So whatever matches this, which is basically a variable name, will go into register 1. Whatever matches the second piece, which is the value, will go into register 2. So we pull off lines from the user, and remember alpha is a pattern, so it has a matcher method, and we can pass it a string. In this case, it's the string that we just inputted from the user, and we get a match alpha and a match assign object. And so we can check the matches method, and if what you typed in was an alpha, then we just call print var and show the value of it. And if you say time equals 20, that's not going to match an alpha, because an alpha has to be beginning of a line followed by a variable name followed by the end of a line. And if it doesn't match that, then we see if it matches an assignment statement, and if it does, well, if it doesn't, we're going to say syntax error, because those are the only two valid options. But if it does match an assignment statement, then we can use the group method to pull off what matched the first pattern, what matched the second pattern. So I'm assigned group parentheses 1 is whatever matched all of this stuff. Not all of that stuff. All of this stuff, including the star. And whatever is m assigned group parentheses 2 matched everything up to the end of the line. And so we say save var, and we pass it the name of the variable and the value we want to save. So type in the name of a variable, we'll call print var to print it out. Otherwise, take the name of the variable, take the value, pass it to our save var routine. And then print var and save var are just wrappers around Hashmap methods, basically. So if you want to print the name of a variable, just say get. That returns an integer. If it's null, it's undefined. Otherwise, print out the value. And when you want to save a variable, just call the put method on the hash map, put that value associated with the variable, and you're done. So you get all of this functionality if you can run it. I think it's about 20 lines of Java code. So as we're talking about different classes in Java, right? Somewhere in the back of your brains, be thinking about what you can do with these things, right? And as you're working on other projects down the road, SLPs or capstone projects at a university or whatever, right? You don't have to continually reinvent the wheel. Okay, it's fun to do sometimes. I love going back to basics and kind of building everything by hand. But if your goal is to do something at a higher level, right, you have access to a lot of these lower level things. Don't be afraid to take advantage of those. All right, does that make sense? talk about compression. So how do we compress files in Unix? You can do a gzip, right? Gzip compresses. No, just first order. That's what you do, right? What's a good file here? So, futon frame assembly instructions.pdf. Well, that sounds good. So we started off at 998K and we shrunk down to 938K. It's a smaller file, right? And it's lossless, right? When I unzip, I'll get back exactly the original file. And we gzip it again, and we get 938,684 versus 938,522. Actually got bigger when we gzipped it again.
Doesn't that like break stuff? Zipping to me twice?
Should be able to unzip it. Because for the most part, compression routines don't really care what they're zipping. They're getting strings of bits. And it could be text, it could be an image or a movie, or it could be a zip file. It could be an executable. It may complain if it detects something that it doesn't want to play with, but it definitely shouldn't corrupt it, right? But what if we do this again? So 938, 853. So did it get smaller? No, it got bigger again. That's good.
So it was like tagging information.
It's doing something like that.
If you zip it up enough times, does it get bigger? Then you
I don't know. We could try it.
It should only take one more.
Well, 'cause I know, I read somewhere about
Yeah.
compressing text files.
Mhm.
It's a bit different than this, but they have to put a tree on the beginning, like a dictionary, to tell you how to unzip it.
Yeah, that's the version we're going to go over.
That might be what's going on here.
Mm-hmm.
Okay.
Can you make a compress routine that always makes things smaller?
That
Yeah.
seems like a logic puzzle. I don't
It
think.
does seem like a logic puzzle.
Because if you have something in one bit, that you can't do it.
If it's one bit, you can make it smaller.
You could just keep compressing the same thing over and over.
Yeah, so if it's 100 bits and you compress it 99 times, you're not going to be able to compress it beyond that unless you get down to 0 bits, which by definition you must have lost information. But what if it's 1,000 bits or 1,000,000 bits? Can you prove that this argument always works? How could you prove to someone like in a court of law that you can't have a compressed algorithm that always gives you a smaller file no matter how big your original file is?
Proof of induction.
Yeah, induction, something like induction. We're inducting downward instead of upward, but it's the same idea, right? If the file size is 1 byte, your compression routine cannot make it any smaller without losing information. If it's 2 bytes and you compress and it's going to get smaller, then it's going to become 1 byte and you can't compress any further. And so you can make an argument for n bytes along the same way. So compression schemes generally do a good job depending on the type of compression and the type of scheme that you're using. And so far we're only talking about lossless compression. There's also lossy compression, where you compress something and you don't get back an exact version of what you started with, which kind of seems like a bad idea up front. But there's cases where lossy compression is not a bad thing to do. So where could you live with lossy compression?
Video images.
Yeah, video, images, audio, things that are being processed by forgiving processors. But not for an executable file that you're downloading from the web, right? Those are bad things. So how do we compress? Here's a common scheme for doing things like images, run length encoding. Well, when you have an image, if you kind of look around, scan the room, one thing you might notice is there's a lot of horizontal lines. Right? This is because we're humans and this is what we do. Right? And if you imagine rasterizing an image, just starting in the upper left and sweeping across to the right, coming down, sweeping across again, and storing pixel information as you do this, every time that you encounter one of these lines, you're going to have basically the same pixel information recorded side by side. So if we imagine encoding color information, right, it's not uncommon to find some particular pattern repeated a number of times. And over here, when we have 7 of these 6s stored, if we could somehow store this as something like that, right, just store the number once and then record how many times it's repeated, that would save us some storage capacity. And so this is something called run length encoding, and you store your information with markers that basically say, is this just being stored once, or is it being repeated? You store a repeat code. So that can get you some savings, and there's a lot of techniques like this. And you can look up the details on zip versus gzip versus compress versus whatever else. Compress doesn't seem to exist in Unix anymore, which is kind of sad, because I always liked it. All right, so we've been talking about trees. Let's talk about Huffman coding. So Huffman coding is a lossless compression scheme, and it's the one that involves storing a tree somewhere in the file so that you know how to read it back. So let's pick out a sentence. So suppose you want to encode the following message, and this is all going to be lowercase. And I'm going to use an underscore for a space so we can see it. So let's encode she sells seashells. Seashore. That's the contents of our file. And we'd like to store this. So 1, 2, 3, 4, 9, 10, 11, 12, 13, 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 30, 1, 2, 3, 4, 5, 6. Should be 37, I missed one somewhere. Okay, so 37 characters. And if we're doing ASCII, we have 8 bits per character. So whatever this turns out to be, 296 bits to store that message. Yes.
Since it's ASCII, can we fit 7 bits?
Yeah, but if we're not being clever, we're just going to use a character for each. It's going to be 8 bits. But it's a key observation. ASCII really only has 128 unique characters. So if we wanted to really save space, we could use 7 bits per character, and we have to pack them into our memory, because our memory is still inherently byte oriented. So we've got 8 bits, 8 bits, 8 bits. But we could store the first character in those 7 bits, and let me call this A0 through A7. Then we could have B0, B1 through B6, and then C0, C1. Pack them together. We can get away with only 7 bits per character, and that's going to save us 37 bits. Another option, how many unique symbols do we have in here? We've got SHE space L AT. And I believe there's 2 more somewhere.
Oh,
There's an O and there's an R.
yeah.
So we've got 9 symbols. Well, how many bits do we actually need to differentiate 9 symbols from one another? 4 bits. So if we want, we could make a new coding rather than ASCII. We could say this is 0000, this is 0001, and so on. Come up with a coding for each of these. 4 bits, 37 times 4. That's going to bring us in at 148 bits. So that's even better, right? Well, Huffman Coding takes advantage of the observation that not all of these symbols occur at the same frequency. The S occurs very frequently. The R only occurs once. So we're using 4 bits to store an S, and that's taking, S occurs 8 times, so that's taking up 32 bits. We're also using 4 bits to store an R, that's only taking 4 bits total. So what if we used a longer code to store these infrequent ones, and a shorter code to store the ones that have to be stored 8 times? So that's the idea of Huffman coding. We're going to use a code with a varying length. And the number of bits we use for a symbol will be smaller for frequent symbols and will be larger for infrequent ones. And the hope is if you set this up right, we may spend several bits storing an R, but we've only got to do it once. But if we could store an S with just 1 bit, that would be a huge win. Because to store all 8 S's would take a total of 8 bits versus 32 if we used 4 bits. But you got to set your code up in a way that makes it reversible. Right? For example, we can't do this. So S is really frequent. E is also frequent. And then H is not so common, so we could make that a 2-bit code, and underscores not very common, so we could make that a 1, 0. Right? This is not a usable code. Why?
S and H share the same.
Right? There's no way to know what this is, because I've got a 0 followed by a 0. Well, this could be 2 S's, or it could be an H. Or if I've got something else with a code of 0, 1, it could be an S followed by whatever that symbol is. So if you're going to do this, you got to be careful. You got to make sure that your code is reversible. Okay, and this algorithm we're going to go through will take care of that kind of automatically. So here's the idea. You're going to go through your input text. You're going to do a frequency analysis. You're going to figure out how often each symbol appears. And then you're going to take the symbols that appear less frequently and you're going to combine them. So you're going to take the two symbols that appear most infrequently and you're going to put those together into a composite symbol. And it's going to have a longer encoding because when you get down to this symbol, you're going to need to know which of the two symbols you combined are we actually talking about. So whatever code we have for this combined symbol, we're going to tack on one more bit, a 0 or a 1. And we're going to keep doing this. We're going to take the frequency of that combined symbol, which will be the sum of the frequencies of each of the single symbols, so it'll be a little higher frequency. And we'll put it back in with the other symbols, and we'll reanalyze, and we'll take the two least frequent symbols there and put them together and keep going. So let's do an example. So let me show you our frequency analysis. So S occurred 8 times, E was 7, underscore was 7, H was 4, L was 4, A was 3, T is 2, O is 1, and R is 1. All right, so O and R are our two least often used symbols. So we're going to combine those, and we're going to make a little tree. So there's R, there's O, and we have a combined symbol which is representing R or O. And we're going to label our branches 0 and 1 instead of left, right, or yes, no. We're going to label left as a 0 and right as a 1. All right, so now RO, these have, let's put frequency down here. So this has a frequency of 1. This has a frequency of 1. RO has a frequency of 2. Right, the number of times we're going to encounter either an R or an O in our original string, right, she sells seashells, is 2. So now we make a new frequency table. So RO is 2, T is 2, everything else is the same. And we're going to repeat this algorithm. Take the two symbols that occur least frequently, and if there's multiple ones, it doesn't matter which ones you pick. So you're going to pick the RO and the T. We're going to combine them into a new composite symbol. So we're going to take RO, and we're going to take T. And T occurs twice. We're going to put that into a new symbol called TRO. And the frequency of this is 4. And again, we'll label this branch 0 and this branch 1. Okay, so why are we doing this? Because eventually we're going to come up with a coding for anything that's a T, an R, or an O. And it's going to have the same coding up to this point. But if we want to code the symbol T, we're going to take the coding up to this point and we're going to add a 0 at the end. If we want to encode an R, we're going to take the coding up to this point and then we're going to add a 1 and a 0. And in O, we're going to take the coding up to this point, add a 1 and a 1. Okay, so R and O, we're going to have coding that's 1 bit longer than the coding for T, which will be 1 bit longer than the coding to get us down to this point. So TRO has a frequency of 4, so our least frequency is A, which is 3. TRO is 4, L is 4, H is 4, underscore 7, E 7, SH. And take the two least frequent symbols, that's going to be A and it's going to be TRO. So put those together into a new symbol. And the way in which I'm doing this doesn't matter. If I had put A on the right, this will work just as well. So there's R0 and R1. A has a frequency of 3, and so A or T or R or O has a frequency of 7. And then remake your symbol table, so now L is a 4, H is a 4, ATRO is a 7, underscore is 7, E is 7, S is H. We're not going to deal with S for a while, right? Which is good, because the sooner we deal with something, the longer the code is to get to that symbol. So S being our most frequent symbol, we're not going to merge that into our tree until pretty late in the game. But eventually we may find some combination of these that occurs more often than S, right? And that combination may be worthy of a shorter code than what S has. But we don't need to think about that. All right, so ATRO has 8, so H and L are our two lowest frequency. So let's put those together into a tree. And this was 4 and 4 and 8. And we'll label that a 0 and a 1. Is anybody completely lost? It's okay. Okay. So now LH has a frequency of 8. So redo your frequency analysis. So the lowest frequencies are ATRO at 7, underscore at 7, E at 7, LH at 8, and S at H. So combine ATRO and the dash. I'm going to run out of space. So dash had a frequency of 7. This has a frequency of 14. Label our branches. So these go away. So now we've got 4 symbols in our table. We've got E at a 7, LH at 8, S at 8, and underscore ATRO at 14. So E and LH get combined. Into ELH. E had a frequency of 7. That's a frequency of 8. This is 15. So E and LH get combined, so now we've got 3 symbols, S's and H. Underscore ATRO is 14, and ELH is 15. All right, combine S and ATRO. So S is H. This is 22. There's R0 and R1. And one more frequency analysis, so ELH is 15. S underscore ATRO is 22. Those are the only 2 nodes left, so we're going to combine those into a super node, which is ELH S underscore ATRO. the frequency which with this occurs is 37, which makes sense because there's 37 characters in our input, and this is all the characters that are available. So to say that our character comes from somewhere in here, well, that's going to have to be the same number as the number of characters. And we'll just label those branches. So now we've got our whole Huffman tree. Okay, now we want to code up our original message. Well, when you want to code something, you basically begin at the root, which is right here. And you follow the path from here to whatever leaf node you're after, right? So all our actual characters, our symbols, are on the leaf nodes. So if we want to code the letter S, well, we start up here, we're going to go to the right, which takes us down this one path to this node, and then we go left along the 0 path, and that gets us to an S. So our S is going to be coded as 1, 0. And E, we start up here, come to the left, that's a 0, come to the left again is a 0, that gets us to E. So this is 0, 0. An underscore, go to the right is 1, go to the right again, go to the left. So that's 1, 1, 0. So what about H? Which way do we go from the root? 0 brings us here, 1 brings us to LH, 1 brings us to H. Making sense? So L, 0, 1, 0. And then A is going to be 1, 1, 1, 0. T is going to be 1, 1, 1, 1, 0. And then O is 1, 1, 1, 1, 1, 1. And R is 1, 1, 1, 1, 1, 0. And so that's your coding for this file. Yeah.
So isn't there kind of like a problem since the heights of both of these like left and right tree of like the supernode is different from each other? Wouldn't it be better if they were closer?
Perhaps, let's see. Well, if they were closer, then you'd have more characters with similar sized encodings, but that's not necessarily desirable, right? It kind of depends on the distribution of your frequencies, I think. So if every character was equally likely, then you'd probably want a balanced tree, so that every character had the same length code. But if you had one character that occurred almost all the time and all the other characters were very unlikely, you'd really want one character over there with a single bit code associated with it. And then all your other ones would start with, say, a 1 and hang off on the right. Does that make sense?
Yeah, I guess it's just, it might not be worth like using an extra bit for like H to be able to save a bunch for
Yeah.
another one.
Yeah. Yeah, I'm thinking pathological example. So like E is 990 times and right, so 1,000 characters, and almost all of them are going to be character E. So if I had to code this up on the fly, I would probably use a single bit for E, right? Which means it's going to represent a 0, which means everything else is going to have to start with a 1. Otherwise, we're going to have ambiguity. So somewhere down here, W, X, Y, and Z would be, and the only thing on the left would be E. And that's going to give me roughly 1,000 bits to code the whole thing. If I have just one more branch here, that's going to bring me up to about 2,000 bits. So I think that's what the asymmetry is capturing. So decoding, right, you can take any stream of bits, and you have to know that you're starting at the beginning of the file. You can't jump into the middle. And as soon as you see a 1, you know that you've got either an S or an underscore or one of these. Well, let's start with a 0. Suppose you see a 0 in the beginning, right? You've got either an E, an H, or an L. And you don't know until you read the second bit. If the second bit's 0, you've got an E, guaranteed. If the second bit is a 1, you have to read one more bit to know whether it's an H or an L. And so you keep reading until you find the code that matches something in your dictionary, and then you're at the beginning of a new symbol, so you start reading again. And if you read a 1, if it's followed by a 0, it's S. If it's followed by a 1, all of the other options that begin with 2 1s, you have to read the third character. If it's a 0, you're right here. If not, then it's one of these. And you read the fourth character. If it's a 0, you've got this. If it's a 1, then it's one of these, and you have to read the fifth character, and so on. But the way this is constructed is designed to give you a minimum overall coding length. And so for this example, if you do the calculations, you end up with a total of 118 bits, as opposed to 148 for a fixed length code. So you save 20%, something like that. Now it depends a lot on what you're encoding, whether this is going to be useful or not. If you're coding human readable text, this is probably going to be a win, because our written languages generally don't use symbols in the same frequency, although I don't know how much that's actually true. I know in English it's true, but I don't know if there's languages that are more uniformly distributed. But in English it's certainly true, right? E is the most common letter, and Z and Q are sort of down there on the list. And we could also code combinations of letters. Right? We could look at things like QU, which almost always occur together, and TH, and things like that, and come up with codings for them as well. So Huffman encoding is pretty common, and you don't need a fixed code just because you're writing something to do Huffman coding, right? You store this dictionary in your file, so that when you want to decrypt it, when you want to uncompress it, right, you read the dictionary information out, and then you apply that to do the conversion.
Would that be more than 30 bits to store that?
In this case, yeah, but it's a very short file we're trying to compress, right? It was just a few sentences, a few characters. But you know, if it's War and Peace, then it's a tiny little bump. But yeah, that's another factor.
Is there like a better way to store trees than the way we do with Hashmap? Hashmap for a tree? I guess so, maybe. I don't know if it'd be
Good.
You're talking about like space.
And the tree is temporary, right?
Yeah.
Right, so it's just for working purposes, for developing this coding. And the coding can be stored, you know, any number of ways in your file itself, but probably in some coded way.
Yeah, I mean, I suppose, you know, since you have a lot of trees, you probably fit it.
Yeah, you got dynamic memory, right? If you're in something modern. So this is a fun algorithm to code. It's fun to play with, see what kind of compression you can get. See how it does on text versus something like an executable file, which by and large is probably likely to have less severe of a distribution skew. Right, it's not going to be uniform, but if you look at a typical instruction set, I'm not sure you're going to see things jump out at you. Like we always have this combination of bits. So that's one example of compression. There's other versions, but this is a good one to work with, and it's tree based, so it's kind of fun. All right, so tomorrow I want to talk about PA5. It's your last programming assignment at Clark, unless I dredge up some ODPs. And that's going to be a group project if you like, okay, optional to work in groups because you're doing a client-server pair, so it can be fun to each do a half and then put them together. And you're also going to present your projects at the end of the term. So we'll set aside a few days the last week, probably starting the day the assignment's turned in, and you can come up and present. And it's also going to be like with tic-tac-toe, it's going to have a lot of flexibility in how you want to implement this. It can be command line based, it can be GUI based. And it's going to work well if we have access to a server that you can get to connect machines to each other. And so a rogue server may pop up somewhere in the next 24 to 48 hours. And I may give you information on that, on how to connect to it. But I don't know anything about it directly. Possibly, but that'll be useful. So we're going to start talking about networking tomorrow, sockets and servers and client models and things like that. All right, so I will see you next time.
What method did Jesus use to make the file layer when you keep compressing it?